Welcome back, guys, and in today's video we're going to find the moment generating function for an exponential random variable. So let's go straight into finding our moment generating function. So the moment generating function, which is written like this, is the expected value of e to the power of t x, where x is our random variable and t is just some variable. And because the exponential distribution is a continuous one, that means that we're going to define the expectation in terms of an integral. So it's going to be the integral from minus infinity to infinity of e to the tx, so e to the tx times the probability density function, like this. Now, of course, because we know a little bit about the probability density function, we can rewrite this. And really, because of course it takes the value 0 when x is negative, we can just integrate this from 0 to infinity, and we can have e to the tx, and then the probability density function here is just lambda e to the minus lambda x dx. Okay, because and if you want, you could technically say plus the integral from minus infinity to 0 of just the number 0, or e to the tx times 0. But obviously this just takes the value 0, so we don't actually need it to be there. Now we need to compute the integral, but luckily it's not that hard of an integral to actually compute. Let's do it. So here all I've done is rewritten it. I've factored the lambda out because it's a constant, and I've slightly simplified the e's, and I've written them as one big term like this. Now what we can do is we can rewrite this as the limit as, let's come up with some variable, maybe I'll call it like theta or something, but it doesn't really matter, approaches infinity. I'd usually use t, but there's already a t here, of lambda times the integral from 0 to theta of e to the t minus lambda x dx. Okay, just to do it properly, take the limit because it's an improper integral. Okay, continuing on, we've got the limit as theta approaches infinity of lambda, and then let's actually integrate now. So e to the power of t minus lambda times x. Remember, this is just going to be the reverse chain rule. You could do it by a substitution, but hopefully we're pretty happy with the idea that this is going to be 1 over t minus lambda e to the power of t minus lambda x. That's what it's going to integrate to. We've still got 0 and theta up there. Close bracket. Lovely. All right, then let's take the lambda all the way out, and then limit as theta approaches infinity, open bracket, and then we can plug theta in and we can plug 0 in, just basic integration stuff. So this is for x, so we've got 1 over t minus lambda e to the t minus lambda times theta minus 1 over t minus lambda times e to the 0, essentially. And then we can actually take the limit here. So this is going to be lambda, and then what are we going to end up with here? So we can see that as theta approaches infinity, either two things can happen. So if t minus lambda is a positive number, then we can see that actually this is not going to converge, so it's no good. The only way that this does converge is as long as t minus lambda is a negative number. Hopefully this makes sense, because if t minus lambda is a negative number, then we have e to the power of a negative times infinity, and that will converge, and it will converge to the number 0. So, and if it doesn't do that, we're cooked, as you know, the kids would say. We can't do anything. So we have to choose a value, otherwise we're just at a dead end and it's just a divergent integral. So we're just going to say that t minus lambda is less than 0 here. So we've got lambda, and then that term just goes to 0. And then we're going to subtract 1 over t minus lambda like this. And of course, we can rewrite this a bit better. We can say it's minus lambda over t minus lambda. And even better, we can say it's lambda over lambda minus t. And again, this is in the specific case where t minus lambda is less than 0, or in other words, t is less than lambda. So let's just rewrite that down, write it down, and just, you know, consolidate what we've just said. Basically, if x has a exponential distribution with parameter lambda, then the moment generating function is going to be lambda over lambda minus t. And the domain of this function, the range of values of t for which this is going to converge, is when t is strictly less than lambda. Okay, and hopefully that makes sense. We can see that if t was equal to lambda, then up here we wouldn't have that much of a problem, but we would, because you'd have e to the power of like 0, which is fine, but obviously then you wouldn't be able to integrate it because you have 1 over 0 basically. So you can't have t equal to lambda either. So t is strictly less than lambda. But this is the result that we've got. This is the moment generating function of an exponentially distributed random variable. Thank you so much for watching, guys, as always, and I'll see you in the next one. Cheers.